Okay, in this screencast, we're going to talk about radians. And radians are another way of measuring angles. Now, we're used to using degrees whenever we look to measure the angle that's formed when two lines meet at what we call a vertex. Then there's this angle between them that we like to measure, and that opens up a whole field of trigonometry and geometry. Why do we want to measure those angles? Well, they help us in all sorts of measurement problems, and so we need to have something to measure them by. Why do we measure anything? It's so that we can communicate distances, and we can solve problems numerically, and this is what mathematics is all about. So we do need a measure of what is the gap, or the it's not really the gap, is it? It's the angle between two lines. How do we measure that? And we've used degrees, and this one here, we might say, well, that looks that might be a 60-degree angle in there. And if we draw two perpendicular lines, then we know that that's a right angle. We might put a little square in there. That's a 90-degree angle. And if we draw a straight line like this, then that angle in there is 180 degrees. It gets you thinking, doesn't it? What is this? What is the why is a full rotation, for instance, why is that 360 degrees? So if you look back through history, then there's a couple of theories. 360 degrees. Well, it takes 360 days for the Earth to rotate around the Sun. So the astronomers early days would have been looking at maybe every day being 1/360th of a rotation, and we've got a calendar now that's at 365 1/4 or something like that. So that's one theory. Another is that in the ancient Babylonian number system, they used a base 60 to do their calculations, and they used equilateral triangles a lot. So 60 degrees was important to them, and you could get 6 of those into a circle. So there's a few. It's a very factor-rich number, 360. 1, 2, 3, 4, 5, 6 all go into it. 8, 12. So it's there's all these sorts of numerical theories for why 360 was used, and obviously we use to this day. But there's a more mathematical way of measuring angles, and that is using radians. Radians are a more sort of purely mathematical measure. And let's cut to the chase and define what a radian is. So again, we're going to draw I'm going to have a go at a circle here, like that. That's pretty good. And I'm going to go right from the center. We're going to construct a radius. Call that R. Now note that radians. There's a similarity in the word there, and that's no coincidence. So what we do there is, what we're going to do, I'll now construct another radius out here like this, obviously same length, and let's call this angle in here theta. Now, let's just say that we have constructed, let's say I'm going to extend these radii out, that we have constructed an angle here between these two radii that subtends, there's a word I'll explain in a moment, subtends an arc length here, that is also equal to R. So what we've done is we've created an angle that subtends an arc length, so creates an arc length, or chops it off, or segments it, so that it's one radius. So what would we call this angle here if we're gonna create a new system of angle measurement? What would we call this angle here? Well, what we've done is we've created one radius on the arc length, on the circle. We've created one radius. So if let's call this 1 radian, because what it does is it makes an arc length of 1 radius. We've got 1 radius. So if we were then to extend that theory out, and that's not such a good circle, in fact, it's an embarrassingly bad one. That's a better one. If we were to extend this theory So that there's my radius. And now let's get our little highlighter pen and get 2 radiuses out across. So let's just try and measure that 1, 2, about there. And we were to chop it off there with our radius. Then this angle here, because this is equal to 2 radii in length, 2 radiuses, then this here, this angle in radians would equal 2 radians, because it subtends, okay, it chops off an arc length of 2 radii. So that's the definition of a radian. That's what it is. It subtends an arc length of 1 radius. So if we get specific and get some numbers out, if I've got a circle, it's my best one yet, of 3 centimeter radius, and I have an angle here at the center of 1.5 radians, then we can figure out from that information what our arc length is, because I'm told that the angle here, my angle here, is 1.5 radiuses at the circumference. So this arc length will equal 3 times 1.5, which will be 4.5 centimeters. So you can see a much more mathematical way of measuring angles, and it's one we're going to start to use a lot of. And it just makes graphing, it makes calculus, a lot of things very much easier. So it's a human construct, but then again, so is degrees. Degrees is always going to feel more comfortable to you, but radians is what we're going to start to use a little bit more of. So let's just have a think about this. Let's now start to look at conversions between them. So conversions between degrees and radians. So let's have a look. If we have, getting a lot of practice at this circle, terrible circle. If we go back and have a look at our radius here, there it is. Now what would we know that all the way around in degrees, we know that this here, the full rotation is 360 degrees. Right, but now what we want to do is work out, well, how many radians is it, or how many radiuses, how many radiuses all the way around there? So if we looked at it, well, we got 1, 2, actually how many do we have? What is the circumference of a circle equal to? Well, we know the circumference of a circle is equal to 2 pi r, so that means that we get, in our full rotation, we get 2 pi radiuses. So our angle at the center here in terms of radians must be equal to 2 pi radians. So what we've established there with that little diagram and that little conversion is that 360 degrees is equal to 2 pi radians. Remember, it's how many radiuses we can fit around the circle. Now for a full circle, that's 2 pi radiuses. Right, we've known that for years. So that means our angle at the center here is 2 pi radians. So here's our conversion. So if you like, dividing both sides by 2, 180 degrees is equal to pi radians. And therefore, 1 degree dividing both sides by 180 is pi over 180 radians. And going the other way, 1 radian, dividing both sides here by pi, will be 180 over pi degrees. Now you might find those conversions quite useful. Okay, let's look at establishing then, therefore, some formulae for arc length and also for sector area. So let's just have a look at arc length firstly. Arc length, which we've already really defined as, right, if we have a look at our full circle again with our radius of r, And what we're going to do is we're just going to chop off an arbitrary arc length of circle and at angle theta. So theta's in radians, obviously. And we know now that the arc length will be r times this angle here in radians. So it's just r theta, where theta is in radians. So there's our arc length. Arc length equals r radius times theta. Very straightforward. What about sector area? Sector area, what's that going to be equal to? So let's go back to our circle and have a look at a sector of that circle. So a sector goes from, what it does is just, it's like a piece of pie, piece of pizza, that there with theta at the center. Then what is this area here equal to in what's its area of what is this sector area? Well, we know that the full area of a circle, we go and look, we know that the area of a circle, area of the full circle, area of the full circle is equal to pi r squared. Here's our r here. But what we've got is we've got theta, we've got a theta over 360, or so if before we did anything to do with radians, you'd have said, all right, I'm going to take my angle here divided by 360 because that's the fraction of the circle that I've got. All right, theta over 360, 360 being the whole thing. You'd take that and multiply it by pi r squared because that's the fraction of the circle that represents this sector. But now we're not going to use 360, we're going to use 2 pi. So the area of our sector is equal to theta over 2 pi, where theta's in radians, times pi r squared. Now we can do some simplifying here, can't we? That pi can go, and we're left with theta over 2 times r squared, or 1/2 r squared theta. So our sector area is equal to 1/2 r squared theta. Okay, we'll pause it there, and we will be doing exercise 5N on page, let me see, page 272 on Friday. I'll see you then.